If not, again, let's thank Professor Lee. And the last topic is from XSKY about when Ceph meets DPDK. We do have some very good news out there, so today it's our great pleasure to hear more details from them. Hello everyone, I'm from XSKY. Today I'm going to talk about the integration of Ceph and DPDK. I want to ask you this. Have you heard of Ceph? If you did, please hands up. Well, not many. So it may be a difficult presentation for you. Let me introduce myself. I'm Wang Hao Mai. I work at XSKY. I'm an active Ceph developer, and I maintain Messenger. And today my topic is about Ceph. There are 4 parts in my presentation. First, what is Ceph? Second, as there are more and more platforms that are faster and faster, how do we make sure that, the hardware has been making a lot of progress in the past years. Its speed has gone up like 5 or 10 folds, but the software is not so fast yet. So what bottlenecks, like when there are network of 4G and so on, and other hardware progresses. And third, I will talk about Ceph plus DPDK. There is this library that's provided by Intel, and then next I will talk about our future work or our roadmap. So first, what is Ceph? It's a development project started in 2006. It provides object block and file storage in a single cluster. Now, it has very high uptake. According to some statistics in the past years, there's more than 50% market share of using Ceph in the backend. That is to say, Ceph has very high adoption rate, and also it doesn't have any lock-in for the hardware, because our purpose is to achieve what the hardware can achieve or should achieve. Like, now for some commercial hardware, it provides support, and also for repair and self-repair, self-management, it has the LGPL open source.
So
in 2014, we were acquired. So basically, it is driven by Red Hat. It is also a scalable, high-performance distributed file system. It is not only a file system, but also a distributed file system that can provide all sorts of different ports. These are the rough introduction to Ceph components. We have Rados at the bottom layer. On top, we have the libraries. Based on the libraries, we can realize different APIs. We have RGW. In the middle, we have RBD, like the local SDA and STB. On the right, we have Ceph. Ceph is a distributed file system with POSIX semantics. What are the uniqueness of Ceph? I don't know whether you have heard about crash data placement algorithm. During data migration, there are a lot of issues. So we can connect location and the placement. The data placement algorithms is to distribute the data evenly. Besides one-time hash, we also have some specific parameters relevant. For example, if you have 3 records, the data will be each node of the records. If the records go broken during the migration, the data will also be distributed to something that is not listed. Comparing to traditional hash, we can save a lot of migration work. Usually, if the bandwidth is really high, it will consume a lot of time. The crash data replace algorithms can solve all of the issues. Next, we will look into the self-internal overview from port to network controller. Then we can see the NIC net card until the kernel. Starting from orange, these are the Ceph. We call it the messenger. Messenger layer is to package the message. Then we have dispatcher layer. The core for orange can complete the 4 basic logics, including I/O, replication, recovery, scrub, and tiering. Using scrub and tiering, because SSD disk is really fast, we can do the migration of cold and hot data. These are the storage logistics. We also have other topics. In gray area, we have file store and BlueStore. File store is relying on the local file journal. On the right, we have BlueStore. BlueStore is developed by Ceph to specifically take advantage of SSD. It is a driver for SSD specifically. We also have the components on the right-hand side. That is the overview of Ceph. You may not understand it so well, but we don't have too much time. Ceph with SSD and high-speed net card. Software is not like network software. Regarding storage, we have also been several hundreds of cycles, but storage very slow. It's not about problem cycles, it's about several US or several hundreds or several microseconds. Such a fast network and such a low disk cannot be in line with each other. So the logistics has to be considered, and it's also what we have to do regarding software. Let's next take a look at performance bottleneck. All the diagram shows how Ceph CPU consumption is. As we may see already, comparing to exposing or the pure network applications, it doesn't consume much network applications, but as it has multiple copies, it do a lot of interactions. It is not only a process of receive and send the packets, it is a very complicated dialogue, so latency is a critical issue. For the kernel, CPU represents a lot of time for I/Os. On the left, you may see the kernel code. On the right-hand side, if you press the more, it equals about 1/3. So for a pure client, it consumes about 1/3 of the CPU. So what are the main kernel bottlenecks? DPDK, you may be clear of the challenges already. Firstly, we have the local connections and the global TCP management. You also need to have the socket API overhead. TCP is what I would like to focus on today. TCP is not only used for the storage network and the server, but also for the mobile devices and long-haul networks. It will be optimized for bandwidth, not only latency, because storage has a lot of latency requirements. Secondly, it is a very modest connection and server. For storage network, it has a lot of bandwidth for Ethernet, but for TCP, it is difficult. When the storage network gets sabotaged, the overall clustering effect will be impacted. For the client, this is specifically designed. So TCP is optimized for the following 4 areas, but not to the other applications. We have all been talking about hardware revolution, but the software, to build the kernel applications, we have a C100K and 1000K, the revolution. But to be more concrete, from past 10 years, from switch to OS to NIC to the packets transmission, there are tons of improvements. How to further leverage its revolution are what we have to consider as software engineer. For distributable software system, it needs to go through several operations. For its hardware, we have several alternative solutions for software. We talked about TCP, we talked about the kernel, we talked about the SSD gap with kernel. So what are the existing solutions? We can go through hardware assistance. We can use the solar flare using TCP offload. We can also go through RDMA using InfiniBand and LCE. We also have Gamma and others. For data plane, DPDK and Userspace is also one of it. We can also wait for further improvement in Linux kernel. Tsinghua University has been some project in fast socket. They want to improve the Linux performance itself. The other question is, TCP doesn't need those much features. They doesn't have so complicated algorithms. So, to those of you who understand storage, in the storage network, TCP has never been used as the mainstream. In the past, it's all FC fiber or the pure direct connect. TCP is not the mainstream application, but until SSD, TCP is put as a very important role. So, in quick summary, compatible and proved are the two pros of TCP. We are also talking about Ethernet is getting more and more important. Even 100 gigabytes net card is awaiting. So TCP together with Ethernet, there are significant links between the two. For the usual Ethernet device going faster, comparing to the specific storage network, TCP is not falling behind. In the past, we used FC fiber connection, but with the Ethernet getting faster, we don't have to use a specific storage network. But the con is that it's very complex. We won't be able to deliver a good design. So the complexity is one huge challenge. For the general purpose kernel, besides using DPDK to run the applications, TCP, if it is good, you can use it to run servers, mobile phones, or others. So we still need to improve it. With a good net card and faster devices, we need to think of how to balance the two, enjoy the TCP advantages, but also have great performance. This comes Ceph. Why Ceph is an important approach when it's used together with DPDK. This is an overview of our plan. We started to do it last year already. We use DPDK to have Ceph in. Generally speaking, it is very similar. We have SRAV relevant to the port. Then from kernel to Ceph DPDK driver. Then from X or TX to go up to a dedicated TCP IP stack. The TCP IP stack is really thin. Then moving up, we have the core reactors to handle the actual memory logics. Coming back, it goes back to DPDK again. Then SPDK, through DMA, it will be routed. So for one package to network, to storage, there is no specific copies. In the past several 10 years, we have never achieved this because the past storage is more in the kernel. From netcard to SSD, we have zero copy, we have uncle to realize all of the logics. To be more specific, how we realize the DPDK driver. On the left, actually we go from bottom up. We have the abstract layer for async connection, for async messenger. It is a combination of several connections. Then we have a network stack. Network stack is a virtualized framework of network, but it is only C++, but it's no specific content. Then on the left, we have traditional POSIX stack. We have several POSIX worker to call the kernel. On the right, we have DPDK stack for compatibility. We also have DPDK worker to call DPDK stack. DPDK worker is not sharing anything in between. There is no logs and there is no symmetries. DPDK worker, if we look at it more specifically, it includes DPDK PMD, ARP, IP, and TCP. ARP was mentioned already. It is going through the kernels, but we also have our own simple ARP protocol. We are also using DPDK RPD library. For TCP IP realization, it's quite complicated, but we can talk about the designing consideration. Firstly, TCP IP, ARP, and DPDK device. I don't know whether you have heard about the C* program. It is a very famous open source CI framework. Comparing to DPDK, they have very deep cooperation as well. We will be able to realize a DPDK solution. It is just very good. We can port the C* TCP and IP stack code, get it integrated with Ceph's libraries. We spend a lot of time to do the integration. So the first thing is, we take advantage of the DPDK library to have the workload. And I will give you a quick introduction later. Then we also port it from C*. We will also integrate Ceph's libraries. These are the 3 steps. Second, we want to talk about event drive. In the Userspace event, we have created a center just like EPO. Like EPO, we can register the event. Third, we have network stack API. For the network stack API, for such a stack, we don't want it to have the general purpose. We just would like to realize the TCP IP for Ceph. So we design something very specific for Ceph. For Ceph workload, Ceph library, and Ceph products, we have it customized. In this way, the TCP IP can be very light.
We have done something like that. We don't have to be compatible to the host protocol set to whatever. We just do whatever with the network. We don't need to have the compatible host protocol. That greatly simplifies the network part of it. It's a shared Nothing TCP. It has local listen table and local connection process. And thirdly, as I mentioned before, it's the RSS. That is, it uses TCP5 tuples to have the RX-TX core binding. That is, if the core of the RX and TX are, if you cannot really do it otherwise, you have to use this protocol and we use the IP port. Then when we connect it, we randomly select it to make sure that they are on the course. We use the port to achieve that. And the next is buffer, mbuff. Other than the network, now then let's look at this part. After the TCP path, and then the application layer, and then to the message, and then the BlueStore. The BlueStore is designed for the, on the left hand side it's the road driver, so it can just take over. And then to support high-speed devices, BlueStore achieves the BlueFS. It is already very heavy and clumsy, and it's not necessary to use the BFS or XFS and so on. BlueFS is very light. It is only for the purpose of managing it, and it has the encapsulation. and it has the allocator to do some of the fast management. And in the third is the data, and just now I mentioned kernel driver, and the right to it is the Userspace NVME library. In the traditional I/O or ALDIO, we have to have the DIO layer and then to the driver layer and so on. They are very heavy. But now, after having NVMe, even though it's still heavy, but DPDK, if it goes through the kernel, it may have declined performance. That is why we need this. Otherwise, it will not be worth it. And next is the Userspace NVME library. It's part of the SPDK, and it's already in Ceph master branch for more than 6 months. And other suppliers are integrating it. Now it is DPDK integrated. From NIC to device, it's been very smooth. And now the drawback is that it lacks the user space cache. Even though people say it has a lot of issues, but its performance is very good. Even though the data cache is lacking, so we need to improve on that. So let's look at the details. From the DPDK worker and then to the stack and so on. And then PG, it's placement group. It's like a data set. And then in PG it goes to the BlueStore and then to the NVMe device. So core to core it can achieve complete logic. This is the improvement. For today's performance, actually, we want it to be better. If you think about the system that was designed in 2006, and now if it's to be converted this much, it's not easy. I mean, if the network is connected, then all the logics will be needed. If you use pipeline, if you use synchronization to convert a conventional software to DPDK, it's not easy. But this year they're going to make a lot of effort to do it. So we hope by optimizing the path we can make it easier. It's not enough. Like pipeline or queue and so on, they are more like traditional kernel design and so on. They do not really make up a lot for the DPDK performance. A lot of the advantage will be wasted. I mean, the performance now is not good enough. And next is a roadmap. For example, core logics. No signal weight. I really like it. And it will have to be fully asynchronized, and also it will use memory. About the second part, it's what we noticed, the RT malloc. I mean, every core may have the buffer, and then we noticed that the RT malloc is very ineffective. It's very inefficient. So now we want to allocate the huge page and manage the core. This is the lifecycle management of the buffer. So sometimes it is occupied. So we need to control it better for different events and accidents. Sometimes the buffer is controlled for a long time. It's not like the network taking a packet and then get rid of it. It has to maintain a lot of information. So for some of the details like abnormal controls, we will need to maintain it. So here's the summary. The storage device is developing fast. We need We need to understand the future trend. And thirdly, Ceph is changing to shareless implementation. DPDK is expected to be, the official repo will be released in September this year. So that all of these things will be more integrated with DPDK, and there are details to work on. Think about hundreds of thousands of lines of C++. But of course, we are already halfway done. And that's all I have to say. Thank you. Thank you for the great timing, and let's see if there are any questions from the floor. Any questions from the floor? Well, okay. I guess most of the people here are professionals of storage and network, and otherwise Intel colleagues. Today we covered 10 different topics, and this is the end of today's summit.